engineer. Also, I am also the supervising engineer for the ministry. You're all welcome.
Thank you.
So, and I believe you will have a good time here. Because our system here, and the great system we have here, that is working and really serving us well. You're welcome.
Thank you. I think it will also be worthwhile for us to also introduce ourselves, since all of us are engineers. So let's do it quickly and
My name is Richard. I work in the
George. I'm an entrepreneur looking at solar as a next option to explore. It's also the place, in our location, it's worthwhile. Where you are based? Abuja State. Abuja here. Abuja. Okay.
Regional demand of Flashpoint Energy Limited. Sokoro. I'm a technical consultant with the MD Abuja district.
CEO, Petrol Service Limited. We are solar mission grouper. Use on World Bank project with area. We have at least one site active. I will have to come at 20 coming soon. Good.
Wow. Sir.
Okay, I'm Engineer Abraham Isa with AEDC.
Abuja here?
Yes, Abuja DC.
Madam? I work with Somen's Engineering. Where are you based? I'm in Abuja. Okay.
From the Abuja Nigeria Limited, we are consultants, engineering services.
If I may add something, he is the brain behind this project.
Ooh, I beg. Why not?
So, the brain behind
Let me also add, he's the brain behind this business. So, my name is Engineer Uchi, and I'm the executive director of Asabao, into capacity building. It's under our platform. Oh, wonderful. Pleasure. Get to know. Right. Is that somebody? That's already.
Okay, you're welcome everyone. My name is Engineer Kabir. I represent M1 Energy. So starting from the solar side, right, this represents one of the energy resources, and it basically works the way you understand solar works, basically capturing solar from the sun and converting it into electricity, DC electricity first, eventually to AC electricity. And what does that conversion from DC to AC, as we know, is the inverter. And for the solar side, this represents the PV inverter. Now the solar is, because solar requires a lot of space to achieve a huge capacity. So as much as possible, we had to optimize the available space available within the ministry. So we used all the car parks across the ministry. So when you approach the ministry, you must have started seeing the installation. We used all the car parks, and we also used the rooftops of all the buildings, all the major buildings, all the 4 major buildings. So all this come together is what made us be able to achieve the 1.5 megawatt peak PV capacity. This in particular is a 50 kilowatt PV inverter, and we have 25 of them spread across the entire site. And the PV side of the system is designed to be decentralized a lot, so that you can easily capture energy from everywhere. And that's why we have 25 PV inverters. Some systems or some large installations, as you might be aware, they might have a single big central inverter, but that is not optimal for this kind of installation. So it's better you have decentralized PV system where you can have different inverters at different locations. It also helps to increase reliability, so that if one spoils, it doesn't mean that the whole PV is lost. So if 2 spoils, most is still running, and so on and so forth. So as such, we have this like this. So for example, in this car park, we have 5 PV inverters capturing everything in this car park. See, the car park starts from way down there to this point. We have 5 of them capturing it. This is one here, and another one behind you. That is another one we got there. That's another one we got there. And the last one is there. So now we also have 2 PV inverters similar on the rooftops of the building. So each of the building tops have 2 PV inverters. So basically we have 100 kilowatts coming down from the roof. So now all these PV inverters, it's not like all of them, their output go to the central location. We actually have to combine them to make it more effective to transmit the power to the central location, and combining them is where the AC combiner box comes in. Sorry, please, you have to give some way forward.
What type of loads are captured and placed on this inside the building? Is it lighting and socket mounted, including ACs? Wow. That's why it's massive.
The system is actually very, very robust. The ministry has around 700 ACs.
Hey.
During the project, we replaced around 400 of them, so that we replace them with energy efficient. There's a lot of ACs involved. That's why the system has to be very, very robust to be able to withstand it.
That means they did an energy auditing.
Yes, exactly. So for the system to be part of the robustness of the system is modularity. Modularity in the sense that it should be, like I described for the PV inverters, if one spoil, it shouldn't affect the entire. It should be modular. It should easily separate it from each other, and that applies to this battery as well, the battery energy storage system. Now for the battery energy storage system, it's made up of 2 main components. The battery themselves, that's the storage. This is the storage itself. Then there's the battery inverter, which is this one. The battery inverter differs from EV inverter, but they are basically the same principle, converting DC to AC. For the battery inverter side, it is converting the DC from the battery to AC. From the PV inverter side, it's converting DC from the PV to AC. So it's basically the same thing. So in this system, the battery, they are made modular. It's not one battery, but modular battery, just like you have a battery bank in a residential installation made up of several batteries. The difference with this one and that one is that this our system here, you can easily take out this one and the system will keep working. But in a residential system with the battery bank, if you remove one, the voltage will reduce, you can't keep work. You understand? But this one, each of them operates, each unit operates at the same voltage. So if you remove one, the voltage is still the same because they are connected in parallel.
These small units are all flat inside.
Yes, that's actually a very, very. No, it's small unit. That's another level of modularity. You open it, you see small stacks. So this is a lithium-ion battery. Obviously, it's only for this kind of scale of project, it's only lithium-ion battery that can do the work. And this lithium-ion battery, one of the main drawbacks is it is unstable at high temperature, or it's unstable at fluctuating temperature. Let me put it that way. If one stack spoil, you can move it, the others will continue, basically. So the battery inverter comes together. This particular one, I think, is rated 350 kVA. This one, together, each of the stacks, I think, is like 70 kVA. Each of the stacks, we call them power stages. Each of them is rated around 70 kVA, but together, things like 350 kVA. So another level of modularity is that they have the battery in clusters. As you can see, this is one cluster, another cluster, another cluster. This cluster is exactly the same as this, but that last one is the biggest cluster of all of them. And the way you have increased the cluster is simply by adding one of these more. Just carry this and add again to increase the battery power. So even as this system is now, it's possible to expand it. So this one has 4. There are 2 at the back. 2 at the back, 2 at the front. This one has 4.
One more time, what do you say is the difference between this battery and
this one? This is the inverter.
Sorry.
This is the battery inverter, converting the DC to AC. And this is the battery itself. This is the lithium-ion battery. There's no battery inside here. This is just an inverter.
The AC output of the combiner,
yes.
And the AC out the station. Where did they go?
I'm coming to that. We'll come to that. But before that, let's look at the bigger one. Basically, how do you know it's bigger is that you just count the number of battery it has here. You see that it has 5. Those other ones have 4, but this one has 5. Another way that it is bigger is that I told you inside it has power stages. Inside this inverter, it has power stages. This one also has more power stages as well. So this one I think is like 560 kVA, something like that. Like 560 kVA. Now, combined, if you add all of them together, that's what actually gives you that 2.28 megawatt hours. When you add all of them together, it's what gives you 2.28 megawatt hours storage that you're seeing on the board there. Same thing applies for the PV.
So this inverter uses a
From this battery. The inverter is, the way input is, the inverter is bidirectional. So you can't say input can change. Bidirectional in the sense that it can discharge the battery, it can charge the battery as well. So if it is charging the battery, the input is actually from the AC side. If it is discharging the battery, the input is from the batteries. So it changes. So
It's not a source of power.
yes, exactly. Exactly. Although it's not the source of power in itself, it's just storing the power. That's one thing I'm trying to make the ministry understand. I even if up to 11,000, how many? Pardon? It's 2.5 MVA. Also, the electric transformer is connected in parallel. When something is connected in parallel, the power does not flow through it. It just taps, and just like the same way saw the restars work. The power does not flow through the electric transformer. That's why you see that it is small. It just taps. So if you look carefully, you see this, each of the connection point has like a U shape. So the power just comes in and goes. It doesn't pass through it. The electric transformer just taps from each of the line and helps provide adequate grounding. The reason why this electric transformer was included is because the protection scheme for the system actually includes protection for the incoming grid supply, utility grid supply. So apart from grounding this side of the system, this transformer is actually grounding the utility grid as well. We have a 300 mm square cable that is going to the utility grid transformer. The electric point in the utility grid transformer, grounding it as well. So in an event of a surge or a fault, this will be able to arrest it effectively. This is rated 56 kVA. Yeah, every component, every AC component, including the PV inverter, the battery inverter, they all work in 3-phase. They all produce 3-phase directly. So all of them are basically synchronized to each other in 3-phase.
enter here.
And they enter here as 3-phase program.
In a smaller scale,
You don't need it.
no, we don't need it, but we use what they call isolation transformer.
Pardon?
Isolation transformer. You can isolate the line from that your distribution network from your generating side, and you can do some work.
Yes.
Yes. So I'm thinking whether it just supposed to be for
And this one is because of medium voltage. If our utility, if we are combining, but I'll explain further inside, or if we are combining the utility grid at low voltage, don't need it. But if we are doing it at medium voltage, a lot of things can go wrong. You have to be very careful.
From my video experience, they are not an active switch.
Active switch.
Active switch. You either shut off or put on.
Yes, but this will only work if there is a surge. And even if the surge is coming from the utility grid, you are arrested. So we can go back going. But it now depends on the type of synchronization. We'll get to that. That one is a bit more technical because synchronization requires all the energy resources to operate at the same voltage and frequency. And there's no way you can predict the voltage of the grid. You understand? So in order for you to synchronize with the grid effectively, that's why synchronization in generators is easy, because you can easily use AVR and the governor to change the frequency and the voltage of the generator to meet the requirement. All of them to synchronize at that voltage and frequency.
So it still switches over from AEDC to solar system. There.
Yes, exactly. So that's why I said you are correct by saying there's a form of synchronization happening there, but it's not the type of synchronization that happens with generator. That type of synchronization is where one source allows the other source to take control, and if that other source goes, it takes over. You understand? So I was saying that
panel has a two input here, input source here, where it changes between one or the other. Sure. The utility grid comes in here, the microgrid comes in here. We can be on the utility grid, we can equally be on the microgrid. It's separate. So it's more or less like a change over panel or something.
I'm not really simple. Very sophisticated. I'm not really.
Can I understand? Maybe an injection station. At that point, an injection station, the injection substation, kind of. Because here now, you see input coming from the grid.
that's why it's important for us to go there.
Yeah. It's a kind of injection substation.
Not exactly a substation, but
Yeah. Sure.
But yeah. Yes. So what I was trying to say in the type of synchronization is that if we go a bit technical, in a traditional solar system, the main what keeps the power stable and continuously operating is actually the batteries. They are like the brains of the system, and that's why these PV inverters actually follow the batteries. So the PV inverters, they don't generate their own voltage and frequency. They are incapable of doing it actually. So what they do is that they follow the voltage and frequency of another energy source, and in this case it's usually the batteries that they follow. Now, and why they follow the batteries, because the battery is able to control the PV inverter as well. But when you're working with the utility grid, there's no way you can control the utility grid. There's no way. So in that, as such, when you're working with battery inverters, they operate in two main modes, and that's when it is getting a bit technical, because one of the way they operate is called grid forming, and that one is called grid following. So that chart here represents the energy consumption from the ministry. The timeline like this is a 24-hour timeline from 0 to 23. Yeah. And apart from that, we have this color code represents when there's high kilowatt hour readings in the meter. Sorry, when there's high kilowatt readings in the meter. So the blue area here represents that there is low loop. There's a relatively low readings in the night. That's from around 0 to 7:30 thereabout. But when the ministry opens up, you see that the power starts increasing. So around 12 they have the high load. This red represents high load, and so on and so forth. So just like the color chart. Yes. So we have various other data. This one represents PV production over certain days, and so on and so forth. So like I said, we're measuring everything.
Another question I want to ask is this. This is 0.5.
Yes.
The ministry demand is 0.7 megawatts.
Yes.
Assuming
if he's bringing 0.2, sir. If he's bringing 0.2,
but you said that assuming this one is off, so maybe there's a very poor.
Let's say it's 0.
It may not be completely
night.
Okay.
In the night.
In the night, it can be 0. In the night, it can be 0. But during the day, it will not be completely cloudy atmosphere.
That's true.
So when it is not able to bring up to this, how does it? How does it measure up?
The battery may even be
The battery can take the
The battery can take the entire load. You stand there alone.
Size 1. Generator is there.
So the battery,
Size is 2.2.
you see all those battery inverters, right? If you add them up, they come to around 1.2 megawatts. They can take the entire.
The ministry is not more than 1. Most case.
Ministry,
It's on yourself.
that's on the dry season when the sun is very hot, when everybody's running their ACs. Can be around 1 megawatt.
They have 1.5, so the same threshold. 1.9 still profile.
We are still in discussion to make sure that those doesn't increase. Because if it starts increasing at an uncontrolled rate, it might start creating some issues.
I still believe that general kind of housekeeping training.
Yes.
Even if it's 10% saving is something.
So,
does that mean the generators are always sleeping?
no, like you can have a long day where rain is falling. This happened this July.
Some few days ago.
Now. You see continuously the sun won't come out, and in such cases the battery is currently 50%. In such cases, the battery will discharge and go below this and go to 30, 20, and all that. So there's something that has to go. This one represents the communication panel physically. So you've seen how vast the site is, how big it is physically. And if I tell you that there is a PV inverter that is in the last floor, on top of the roof, it's very far actually, considering the scale of the site. So how do we communicate with it? Traditional communication will not work. So we have to use fiber optics actually. So fiber optic is what communicate with most of the assets that are far away and brings everything here. And this is the panel that basically is like a substation for the communication. Everything is tracking everything, sending all the fiber optics to all the rooftops, all the car parks have fiber optics getting to them for us to effectively. So if there's something that if the system needs to control the PV power instantaneously, because there is a situation where PV power is high, that means there's a lot of sun. The battery is full and the load is low. There's actually that situation. What do you do with the power? Because the PV power is now excess. There's nowhere for it to go. The battery is full. And the battery is full, load doesn't need load is slow. And that, even though it's just like a simple explanation, that's actually a very, very serious situation. Basically what happens is that the controller will control the frequency of the battery. It will be controlling it between 50 Hz to 50.5 Hz or 51 Hz. So as it's controlling it, the inverter will know that the controller is trying to tell me something, even though there's no communication. So if the inverter sees 51 Hz, it will know that the controller is trying to tell me to reduce my power, and it will act accordingly. That's the frequency control.
But I have a example for you. When you generate excess power, are they no nearby
I wish it was that straightforward. And that happens in the weekend. There's a lot of power that is being curtailed. In a sense, the charge controllers are built into the PV inverters, not the batteries. Yes.
But they can arrange with
That discussion is remarkably complicated. Actually attended to that. Let's go through the battery. So remember I told you batteries have 3 clusters. Also 3 clusters of batteries. So all of them are bringing the power here, each of them. And they're combining at the main bus bar, outside. We'll look at it at the back. There's a section open that allows to see it. But this is a 3-pole circuit breaker, and they are rated accordingly. I think this one's rated 800 amps, 800 amps, 800 amps. No, local thing. 415. I think the standard is 400. So this is for the battery. Presents the battery again, metering and monitoring it. And this is the meter here, monitoring the battery. This section here represents the PV. And remember I told you when we were in the car park that the PV is divided into 5 groups. Combined into 5 groups. And it's just 5 groups you see here. So this is 1, 2, 3, 4, 5. These ones are smaller because the PV in that area is not that big. Like for example, this one represents 7 inverters. And this one represents just 4 inverters. You understand? So that's how they are rated. So this represents all PV inverters that are from this section here. This is the segment of it. This is for generators. And of course, generators are off now, but the generators are off but remain connected. Because in order for the generator to synchronize with this bus, it must be able to read the voltage and frequency on the bus. You know, the generator has its own voltage and frequency. It now has the bus voltage and frequency. But to be able to synchronize the bus to the bus voltage and frequency, it must be able to read and effectively read the voltage and frequency so that it can synchronize. It's written on the circuit breaker. Yeah, it's changing there. So this is an auxiliary panel. The auxiliary power supply. Auxiliary power supply. Yeah, so basically if the bus bar dies, the main panel dies, this provides power to all the communication equipment so that they keep running. Because it's only via those communication equipment that can come back online. So you see a section of the panel that is open. Okay. So this section is, I think, it's one of the PV sections. And you see that, okay, let me move here. But you see, the main bus bar is the one that is running on top. That's a 4,000 amp bus bar. And this smaller, this is at 500 mm square cable I told you about. That brings the PV to this room. 500 single core. That's single core per phase, or one run per phase. This is a yeah, this is a series of protection. This is the neutral bus bar, and that's the head bus bar. So periodically we conduct, we analyze the grid. Basically, we analyze the power quality that is going to the ministry, and that is what we are doing now. Some of you might recognize this. This is a Blue 435 power and energy analyzer. So what it does is that it monitors total harmonic distortion and voltage frequency. It monitors the current distortion, the current harmonic distortion, voltage harmonic distortion. It monitors energy and all the power parameters as well. So kVA, kVAR, kilowatt as well. Everything. And you can, once it finishes monitoring, it records it, and you can do analysis and see whether something is having problem. Maybe the power quality is not too good. You need to adjust some parameters. So we do this occasionally. That's why I see the meter is connected. Everything. Basically measures almost all the power parameters. Everything.
Please,
that's why.
Do you have to like power factor compensate your equipment?
No. Our power factor is still relatively good for the system, and the PV inverters are capable of doing power factor compensation. PV inverters. So if there's need for it, the inverters themselves will compensate the power factor. Yes. But this is the brain of the system. Start doing it, that's when it becomes evident that they are replicating it.
Things are agreed that is a problem. And the schools.
The schools are
you have the capacity to rent more.
One of the headaches
And there's no village there.
This school.
Give out.
is the policies to have in place. You need to change.
But some discos are good, like Kaduna, Kano. They actually give concession to mini-grid developer. My friend didn't tell me that one. They say, can you do it? Oh, come on, we sign agreement.
You sign agreement and all you have to do is just pay them a portion.
No negative stuff.
Well, the developer will get a permit now. So you must get a permit or something. You know, license.
I think the only issue is the power purchase agreement.
Yes.
So if you have a vehicle like an SPV that can
Take it.
Yes.
So now the school will allow you.
They will allow.
How about the other ones?
They will allow because the only thing is the discourse are not testing the regulation itself.
Yes.
So if you approach the regulator, they will allow.
Yeah, sure.
Because all they want is that their money coming into that what they call waterfall. Because their accounts are escrow. So any account money entering the disco will not come out.
Yeah.
So if you can now have an SPV arrangement that you have outsourced that place to the vendor, he does the collection.
And
So you're now giving him a bill.
percentage.
You're giving him a bill.
The license.
Yes.
So he's paying the bill now. He's going into
Yes.
the market. So
Yes.
the disco has no issue. The
Yes.
regulator will not have an issue.
Yes,
only one
to explain it better,
Well,
in that case, in that scenario, the mini-grid developer now that build a grid tie with, to the disco will now be a kind of off-taker from the disco. So whenever your power comes, I'll pay you. So that's what they are doing now. So the mini-grid developer will be an off-taker of the utility or the disco power that come to the system. Yes.
I think there is a policy on that already. That discussion was on sometimes back, and the NEC official said that there is that policy existing already. That generate and sell, give to the grid. But the process of achieving that, we need to find out. And that policy is actually
So just a point to note, although we do not export to the grid, we do not export power, but the system, as it is built, is capable of doing it. In fact, if we want to do it, just to change some codes, here, and power outside the grid, obviously regulation and all the fine things.
Okay.
You can see two green ones and one white one.
What is the capacity of each one?
Big ones are 1 MP each, while the small ones 0.5. That's 500 kVA. Yes, so and all of them are working automatically. They are able to synchronize and work automatically. Although they were existing generators, we just had to upgrade the communication and control system. Had to upgrade it and implement some additions to the generators to be able to communicate with them and control them. That's what we did. They really need to spread this one goes up and that one is data sheet. But unlike the other panel I showed you here that was this one of the latest technology. You can see how slim it is. Yeah, very small. Bigger, fatter one. In those days. Yeah. Unlike the other panel I told you that was assembled and constructed here locally, this, on the other hand, had to be constructed offshore. That's because of the rigorous testing that is required. So it was basically shipped in cubicles. So what we did here is just to operate the cubicles. So this represents the 11 kV switch gear, and this is obviously a replacement from the old one. There was an old one that was here initially. The old 11 kV switch gear was, it didn't have protection, it lacked some breakers, it was basically very, very good. And it couldn't do anything that it couldn't allow us to integrate the system well enough. So there was a lot of barriers to using that one. So after some engagement, the ministry decided to replace that panel. Replacing this panel, we made it a bit more robust. So there are two main inputs to this panel. The first one is utility grid, which is this side here. This is the utility grid incomer. This is the ADC incomer. ADC is currently not available, but this is the incomer. Then the output of our transformer that we saw there is coming here. It's coming to this section here. That's the microgrid. And you can see it is available because of this red light. This is not available. There's no utility grid.